This presentation is focused on explaining code I wrote for implementing a Bluetooth GATT server on an Arduino, and that code's available in this repository here. To do that, broke the presentation into three parts. First, discussing what are Bluetooth GATT servers, and then take a look at the code, which is this one file, and finally show a demo of it. In the notes, I'll have the times of these remaining two sections so that you can skip ahead to different parts. But first, what are Bluetooth GATT servers? And the way I like to think about it is first start with the use case. And this use case will be what I actually implemented in code, and that was a counter. And so for this counter, I wanted the counter to always be an increasing counter with a minimum and maximum values that were adjustable over Bluetooth and between 0 and 255, so 256 levels. I wanted to also be able to know the status of the counter over Bluetooth, so whether it's stopped, started, and I wanted to also control the counter over Bluetooth, so being able to stop, start, and reset it. And I wanted the counter step to be adjustable in seconds. So every time it incremented by 1, I wanted that time to be something that I could set in seconds to make the counter go either faster or slower. So to look at how this relates to Bluetooth and GATT servers, if we take those requirements and just kind of focus on one of them, of wanting that counter step to be adjustable in seconds, we can relate and map the requirements of what I want with this counter to the Bluetooth GATT server world by thinking about these requirements and breaking them down, and first breaking them down to very basic parts of words. And in the Bluetooth world, we're going to see that these words, so for example, the counter step, are going to map to something called attributes. So those are the fundamental properties in the Bluetooth GATT server. We'll then combine, just as we combine words here into phrases, that we'll see that multiple attributes can be combined into characteristics. And then as phrases can then express a more complex idea as, well, sentences, and combine to form paragraphs, that these characteristics can then describe a service, and the service for us will be that counter. And multiple paragraphs then can be combined to form a cohesive story that could have multiple parts. One paragraph could be talking about the counter, another paragraph could be talking about how it applies to, let's say, a heart rate service, and all those services combined together. So if you think of paragraphs of services, where you could have paragraphs telling a more detailed story of a user being able to do something, here the Bluetooth services combine to form a profile. Now, for the example I wrote, I'm not going to deal with profiles, so our story ends right here. We just focus on the paragraph of this one particular service, this counter. And with that, we'll see that the storage of this information of the base words, the lowest level attributes, and that are then combined to form characteristics and then a service, is stored in something called a GATT server database. And this, we'll go through what this acronym here means later on. But you can see in the database, so on the Bluetooth device, that there's the characteristics are going to be made up of attributes. These are this thing called a descriptor, and the values and properties, these are all separate attribute words. And then these characteristics, multiple of these, are combined to form a service, and then these services can be combined in the profile. Now, when we want to map this in using the Arduino tools, I use the Arduino BLE, which stands for Bluetooth Low Energy Library. And the two main classes that I used was something called a BLE byte characteristic, and that expresses these phrases here, so it expresses one of these. And then the BLE service, which can be thought of as this paragraph, so that's a wrapper for the characteristics. And those are kind of the core classes that are used. If we then focus now on what are some of the details about the attributes, we can start by translating this counter step to an attribute. So how do we do that? Well, the attribute in Bluetooth, first we can look at what the counter step is, and that's the counter step size as far as time, so how quickly the counter steps between values, so from 1 to 2 to 3, and that time to do the step will be in seconds, and it can range from 0 to 255, so as fast as it can, to very, very slow inclusive. And that means that there are 256 unique values that can be stored. So that makes up 1 byte. Now in the Bluetooth world, they call a byte an octet. And there's a reason why, because there's some different, even though I always think of, like in the internet world and everything, a byte is 8 bits. You can look at other standards where a byte is not necessarily 8 bits, but can be the word length of a machine. So this occurs with, let's say, like TI microcontrollers, some of their, I believe, C2000 series. A byte's actually 16 bits. So I'll use byte and octet interchangeably for the rest of the presentation, because the Arduino libraries refer to bytes, and in the Bluetooth standard, if you read it, which is openly available and can be downloaded, it'll refer to it as octets. So a attribute is composed of 2 parts. It's composed of this value, but in the Bluetooth world, we want to be able to uniquely identify this so that everyone in the world knows that this particular value is associated with this counter steps, this service and this counter step. And the way you do that is, or the way they chose to do it, is to use something called a universally unique identifiers, UUIDs. And this is a standard that's used in the IT industry. It's used in different operating systems, such as Windows. And what it is a 128-bit number. It's easy to generate. There's a lot of utilities. You can type UUID at the Linux command line. It'll generate one, and it's just they're randomly generated, and they're said to be quote-unquote guaranteed unique because it's such a large number that if you have a good random number generator, that it's extraordinarily unlikely anyone will ever generate that number again. So I did that. I just generated one randomly, and this happened to be the number I got. And this number's in hexadecimal. For people who aren't familiar with that, that's just where every 16 or every digit has 16 values, so it counts from 0 to A, B, C, D, E, and F, and so that's 16 values for every one of these digits. That's a power of 2, and it maps nicely to the binary or computer world. So for this counter step, the attribute, which is composed of a label, type label, saying that, oh, this is a counter step, and then the value, which we have 1 byte or octet. If we take this attribute and look at it in the broader picture of Bluetooth, that when it's stored in the database, there's 2 other parts associated with it. So we have the type and the value, but if we're going to store it, there's what's known as octets and handles, and then value permissions. But we just refreshed the type, and to add a couple more details about this. We just chose, I'm showing the full 128 bits. Often in the Bluetooth world, you'll only see 16 bits, so that would be 4 of these hexadecimal numbers. And when you see that associated for the type, that's a very special UUID, and the UUID will always have the form in blue. So it's this one particular UUID that the Bluetooth committee, called the SIG, chose, and if you see this, so you never want to choose this for what you're creating for your IDs, because this has already been selected, and then it allows them to shorten it to just provide 4 hexadecimal digits, or 2 octets, 2 bytes. And when you see that 2 bytes, you know that that's one of these special numbers, and you can look it up, go onto the Bluetooth site and download documents that say what these labels, unique labels, map to. So that's the difference. Because I made mine up, I'm using the full 128 bytes. And a attribute, my value is only 1 byte long, but you could have up to 512 bytes, or 512 octets, and that could be useful if, let's say, you're storing a string, maybe a very small image, some other more complex binary data. And this handle is associated when this is actually stored in a database, that the handle is a way to index this position. It's a shortened position. Whoops. And it allows you to have the range can go from 1 to FFFF, which is around 65,000, zeros reserved. And the other part is this ID number, which is this index into the database for a particular type and value, is unique, is unchanged for the connection, so that when 2 Bluetooth devices connect, the handle will be unchanged, that you can guarantee that, oh, I know that for this one particular type that this will be stored in this position. Also, the attributes, when stored in the database, can have permissions, and those are defined by the in this GATT layer, which are profile, which we'll talk about more later. But the permissions can have things as to whether this is readable or writable, to whether encryption is used for the value, whether it requires authentication, so that you need to be able to provide some credentials to access this, or if you have been authenticated, whether you're even authorized for that particular authentication or user to actually access this. And so the value permissions and the handle are more associated with this attribute being stored in the database, where the type, which is the label of the attribute, like the key value pair, the key and then the value, are more just associated with being an attribute of data. So we've talked about attributes, but how do attributes combine to form characteristics? And a characteristic is made up of at least 2 attributes, possibly 3 or more. The first attribute is a descriptor of the properties of the value attribute. So the characteristic, you can think of a characteristic as a value that you're storing, but with more metadata information describing the value and its properties. So all characteristics have an attribute, and you see here that it'll have some handle of location in the database. The declaration attribute that describes a characteristic always has this 4-digit hex digit UUID. So this is the special registered one with the Bluetooth SIG, and that 2803 means that this is a characteristic attribute. And that then allows you, if you see that, you know that, oh, the value of the attribute is broken into these three parts: the characteristics properties, the value attribute handle, that means where the characteristics value, that handle right here is, and its UUID, so which actually also then would map to this too. Having both the pieces of information of the handle and the UUID allow you to do some searching more quickly without having to do looking up the value from the handle. The permissions for the characteristic, the declaration attribute, are read-only, no authentication or authorization. What this means is that any Bluetooth device, Bluetooth low energy device, can find out the characteristics, the declaration of all characteristics on another Bluetooth device, because they're always read-only and they don't require any authorization. And what they can't see necessarily is what this actual value is. So they can know what data it has, what the labels are, like, oh, this has a counter service on it, and this has a counter value and other properties. So it can know what the attributes, what their description is, like what their labels are, but not their actual values necessarily. So the other part of the characteristic is the attribute that contains the value, and that also is made up of the handle of where it is in the database, its attribute type. So for the example I gave, that would be that UUID that I made up, I would put right here. And then the characteristic value, so for my counter step, that would be that 1 byte value. And then if I wanted to do different permissions, I'll have read and write permissions, but I'm not going to have authentication and authorization. And finally, there's descriptors, which can be one or more. And those descriptors, describe the attribute. There's the important one that have is something called, if there's notification and indication, you have to have this. And what that means is, if this value, if the client, so the client is the Bluetooth device that's connecting to this database, if the client says, hey, I want to know when that counter changes value, it can set in the properties here that the characteristics, like, well, if this is set to be able to allow notification or indication, then the client can then say, yes, I do want notification and indication. So as soon as this value changes, I want to be notified by it or indicated by it. Now, what's the difference between the two? The difference is that notification is where the device that has the counter in the database, where it just simply tells the client, hey, the value's changed, and it doesn't care if the client responds back that, yes, I got the fact that that changed. Indication requires that the client reply back and say, yes, I got your message that the value's changed, and if it doesn't get it, then it will resend it. So this, and I'll talk about this actually on the next slide. So again, we have that characteristic declaration attribute, and we'll go into a little more detail about it. That fact that it's read-only, so any client device can connect to it and read like what this is. This is just a little more detail here about what the sizes are. So the properties, the value of the handle is 2 octets. So this handle is 2 octets because that's how it's only 16 bits for all these attribute handles. And then the UUID here can either be the 2 octets if it's a special Bluetooth one, or 16 octets. Now the properties is interesting, and that's something that you can set with the Arduino library. Specifically, the ones that focus on are the read and write, which I'll talk about. And so that's whether the client can read the value, not the declaration, but the value, and whether it can write that value. And here's the notify, and this is the server saying, if this is set, hey, the client has the option to be able to be notified. And if this is set, the client has the option of being able to be indicated, but the client has to choose that. Those properties are in the Arduino BLE library, are represented by these enums. So when you see these enums, whoops, that's what they're referring to, or these properties. You can see that the actual values are set right here, and that's so for like indicate here, that's hex 20, and then these correspond, 80 corresponds to this bit shift, which I imagine they're doing because that way it can prevent if there's signed issues. So if we look at the value of the characteristic and how we set that in the Arduino, what we see for that, the characteristic value is a single attribute. It has some handle that can't be set by this API, but that's configured on the Bluetooth controller. But the attribute type, this is the attribute that I chose, and we're just going to set that, so that gets set there. And the attribute permissions can be set, although I don't set them, but those could be set in the Arduino library with these enums. And when we go to actually change the value of the attribute, we use the write value function. So you create the characteristic, an object of that class, by specifying what the label is, saying that, hey, this is going to be my status. In this case, we're talking about status and not the step. And then you can then set the values with the write value function. So the permissions part right here, that's actually handled with the reads, and that was the properties here. So our read and writes for setting whether this attribute is readable and writable. And what this says is that the client is able to read the status, but it can't write to it. It's also saying that the client can get notifications if it desires from the status, and so these are what's being set here. And those notifications, that's that third attribute that can be associated with the characteristic. What the client would have to do would then say, yes, I want to be notified by setting that value. Okay, so we've talked about that attributes are the base level, characteristics are made up of multiple attributes, and services are made up of multiple characteristics. And to be able to create a service, we need to know what all the characteristics we are going to have, and this is just codifying that cloud that I created earlier by saying that, oh yeah, the current value, it's going to be an unsigned byte that's read-only, and then for the inclusive, we'll have minimum value and a maximum value, and then the step is adjustable, so that step time will be an unsigned byte that's both readable and writable. The minimum values I wanted readable and writable. I wanted the current value to be just read-only, and then I wanted commands, so I wanted a 1 byte that's writable for the command, so you can't read the command. But when you write what the command is, of let's say start, stop, or reset, so these would be integers that are signed in the code, that command status is readable by the client at any time, or the client can get notified if it chooses. when the value changes. And here, for wanting to know the status of my counter, that is 1 byte, and it's again readable with notification. To be able to take this and map it to the Arduino world, we can do the service implementation here of deciding. So the basic procedure that's done is first deciding a name and UUID for the service. I called it ramp because I thought of like, oh, the counter's counting upwards like on a ramp. So, and 1 means it's I have in the code two of these ramp counters, just demonstrating that you can have multiple services doing the same thing but are different counters. And they have to then also have, the services have to have different UUIDs. So for this first one, this is the UUID I chose, and then each characteristic has its own UUID. So then you create all those characteristics. These would each be the characteristics of the commands, the step time, and all that. So you create a bunch of those, each having their own UUID, and like for example this one, and whether they're read, write, notify, and all that. And then you take the characteristics and you add them with the add characteristic to the service. So you do that one by one. And once you're done, you register your service. So we take our service and we add that to the BLE object, and then we advertise it so that other devices know, hey, there's this service available, and they set the interval. So that's like it's a multiplier. It's about every second, having the comments about what that number corresponds, how it maps to seconds, and then start advertising. And now devices can connect to this this Arduino, and they can read all the characteristics. So they can't read the values necessarily if I've done authorization or authentication, but they can definitely read like, oh, it's got a current value, minimum value, maximum value, step time. So it can read all those facts, but not necessarily the values themselves of what they are. Okay, so the next part details what actually happens behind the scenes. It's not necessary for understanding the Arduino code base itself. So if you want to just either skip to the part where I go through and explain the code and do the demo. But if you're curious about when I do the demo and show the capture of the demo, what's going on, this just talks about the over-the-air information about how this information is transferred. So we have our device that has a service on it, the counter service, and that is our LE device. And then we have, so the LE is low energy, so Bluetooth low energy device, and we also have our client, and our GATT client. And this GATT it's a way to set of rules to be able to say how it defines how this protocol works and all that. And so it's oriented by the client, so the device that connects to your counter service. The client drives everything pretty much, and so the client can either issue commands over the air, it can issue requests for data or information, and when it issues a request, the GATT server, your device, has to respond back. You can also, if the client's enabled, issue notifications when values have changed. You can also have indications when values have changed, where the client needs to confirm that it got those. And the basic flow is the client reads from the server, writes to the server, and it can search the server. And those are the things that it can, interactions it can have. Now, some of these actual commands that are sent over the air, they take the form of the name of those commands. the PDU is the data payload that's sent. And so these command names, you can be asking for information, starting handle, ending handle. This is when we had those handles associated with the attributes. This is useful because you can just specify that 4 hexadecimal or 2-byte handle of where to start and where to stop to look. And then when you read a request, you can just ask for the handle and not have to ask for the full 128-bit UUID. And you can then, so you can read a request and get a response. So you ask for the handle and then you get a response back of the value, and I'll demo some of this. And then you can do the same for being able to do write request and write response, and that request response is this information here. And then you can also have some attribute handle commands, and there's more commands too than just this for things with errors and finding data and that. So to see how it sort of all ties together, look at a little more detail of what an actual database looks like. We have our devices right over here. This is the device, like your phone or whoever that wants to interact with your Arduino. And this could be in a sensor roll. We're just doing the counter. If you look at the database, what you see is pretty much always you're going to see this order, where the very first element is what's called the generic access profile service. I'll detail that a little more, but we see that we have these characteristics. So the characteristics are made up of multiple attributes. So the attribute is one of these lines. So one of these rows is an attribute, and then we're kind of indicate here, this would be actually here and here would be one characteristic, or actually, sorry, this would be one characteristic right here. This is the service identifier, and then this is one characteristic. This is another characteristic made up of 2 attributes, another service identifier, another characteristic made up of 2 attributes, or 3 attributes actually, and then another service identifier and additional characteristic. And talk about these a little bit. One thing is that we see here that since these UUIDs are the 4 digits, that they're the special ones that are registered with the Bluetooth SIG, and you can look those up to find out more details about those. Those are defined in detail. That's one nice thing about the Bluetooth is that the documentation is all freely available, and I think it's really well written as far as standards go. The other thing is that on the database is that we have here with the service, when we look at one of the characteristic declarations, we can see that this says, oh, the value handle is 03. So this characteristic declaration is for this particular attribute, which is the device name, which happens to be Arduino, and the permissions are read-only permissions. And here, this is also a value handle for appearance, and these are standards with this profile, and so that appearance is default of 0. We go to our next service, which is the GATT, and we'll talk about these two in a little more detail in the next slide. But the characteristic declaration is 08, and that's, or the first characteristic in this service has the value of 08, so that's the service changed, and that's another standard, so that you can it has an indicate permission, which means the client can set this value here and say, yes, I want to know when services have changed, and so that's why it has 3 attributes for this one characteristic. And this, finally, we get to our service, which is right here. And then we've got our ID number, UUID number that's stored in the value, and that is primary service. And we can see that one of the declarations of the value handle, and it's a read-write. And then we have it's C, which happens to be one of the ones we define for minimum value. And we'll actually see these numbers when we look at the Arduino code. But this is on the, this would be on the Bluetooth chip, controller chip is where this, or actually at the host level where this is set up, on that Bluetooth chip. So if we look at the mandatory services, those two that had mentioned with the GAP and GATT, the GAP service, which has that registered name, that specifies, if you look in the Bluetooth core spec, it talks about what all its rules and what all it does, but it has all the characteristics for whether the Bluetooth device is acting as a broadcaster or an observer, peripheral, or central. And these are basically whether it's just advertising or it can be connected with, which is peripheral and central. And it must have that device name and appearance, and that's what we saw here, that they must have that. And there must be one of these running on the Bluetooth device. Now, this thing that we've been seeing with this GATT service, which is the generic attribute profile service, it indicates if the device supports robust caching, and some indications of additional details that it supports. And there can also be, it also controls like the rule sets for how data is sent across there. There's only also one running per GATT server. Some additional UUIDs that we may see besides primary service. So these are those that we may see, and just as a reminder that if you wanted to know what the full UUID is, you would take these 4 digits, plug them in here, and then for this special UUID number. So now let's look at some code. This is reviewing the code that's on the GitHub site, and it's expansion of what we were talking about with the GATT server service. And the way the code is set up, first we declare a service using the random UUID I created. So for the ramp counter, this is just, I created the random number, and then because I'm going to have an identical ramp counter, a separate independent counter, just incremented this by 1. Figured that since this was random, incrementing by 1 would also not collide with anybody else's UUID. These are the commands that you can issue: the start, the stop, or the stop, start, and reset, and then what the result of the commands were, and the status result too. These are the characteristics for the counter. So we have the minimum and maximum values of the counter. What the current counter value is, that's read-only, so that can only be read by the client device, but the minimum maximums are read-writable. The command, the client can write those stop, start, and reset commands, and then the client can read the status or be notified of the status, and along with the command status too. So that whether this would be the status of whether the counter is running or stopped, and this is the status of trying out of issuing the command. And then the step time is right here, and that is writable only, or writable and readable. For the second independent counter, we have the same characteristics, so the same characteristic numbers used, where I randomly generated the UUID, then I just incremented it by 1 to keep it organized. But these are different instantiated objects from the characteristic class. All of these are byte values. The setup is that if talking over the UART or over the USB port with the serial, then having this set to a baud rate that you want, If you're running it standalone on a battery, having this commented out is important. Otherwise, it'll hang on that statement if it's not connected to the USB port. This just sets up the LED as an output, and that this just starts up the Bluetooth low energy module, sets the name that will be advertised for the device. These add those characteristics to the first independent ramp service, and then adds the service to the Bluetooth device. These add those characteristics to the second independent ramp service, which then adds it to the Bluetooth device. We then advertise only the first independent service, that we advertise to the world that this service with and it advertises this UUID out to the world that's available. Then we set the interval for a second, so every integer value is 0.625 milliseconds, so multiplying by this will give a second of advertising. It'll advertise over the 3 Bluetooth low energy advertising channels, and then just wait for the connection. So in the loop that's continually executed, this waits for a connection. If it's connected, client connects to this GATT server, then we set up the default values that no command's been received. Just put some default minimum maximum values and set the minimum counter to 1. Don't have the counting start yet, and then just set the step time to 1 second per step. Then set the LED state to high, so turn on LED. And while it's connected, if there was a writing if the Bluetooth client wrote a command, then evaluate the command. So grab that command, and if the command's a stop, write the status that the counter stopped. So if the client has notify, it will get this as a notification, and also write that the command was successful. To start, and start the counter and write that the command was successful. For a reset, and just reset to default values, and print an error if there's a problem. That's if the unsupported command was received. So if this looks at the status of the counter. If counter 1 is running, then can print the value and delay for the number of step time in seconds. And then if the counter has rolled over, like past its equal to its maximum value, then reset the counter back to the minimum value. Otherwise, increment the counter, and then toggle the LED. And then finally, when it's disconnected, and just turn the LED off. And that concludes the comments for the discussion of the code. Now we'll look at a demo. So for the demo, what's the setup is, we're going to have a VM that's running the Linux Bluetooth CTL command line, and that's going to act as a client. We're going to first, and then that'll talk to a little Bluetooth dongle over the USB port. And we'll also have our Arduino that has our GATT server database, our code running on it, which creates that, and then our little ramp counter. And so those will be running. This will start to advertise. This will scan, we'll pick up the advertising, we'll connect to it, and then they'll transfer information, and we'll set up we'll reset the counter and look at that and just play around with some values in the Bluetooth client. And then we'll also look at the over-the-air capture. And so the devices used basically will have the USB dongle connected to the Linux VM, our Arduino, which is connected to a USB battery supply. This is just as a kind of fun side note. There's this product called PowerEver, which is on Crowd Supply, and I think they're still selling them, but I had gotten some of these a long time ago. What's cool about them is if you have a low power device such as your Arduino, and you connect it to a normal USB power bank, what will happen is this will sense that if this doesn't draw much current, it'll sense that and it'll think that the device is done charging, so it'll just shut off the device, and you don't want that. So the solution to that is, well, two solutions. One is you can either have like a lossy resistor network that's always drawing a large amount of power and dissipating in its heat, and then that'll keep this on. Or you can use this device, and I believe what they do is they basically have a little transistor acting as a switch, and every so often it sucks, it turns on and drops some power, and it's enough power that this still thinks that the device is charging, so it will not shut off. And it works out pretty well. Like I've used this on a few devices and haven't had any problems with it. The over-the-air capture will be done using a Teledyne LaCroix Frontline X240, and I'll show you the wireless protocol suite software for doing the capture, and then it will capture the traffic there. And let's look at the actual demo. So for the demo, I'm going to start with Teledyne LaCroix wireless protocol suite, and I'm going to start recording the what we're going to do, and then so that's going to capture the over-the-air traffic. And now I'm in the Linux VM, and I'm going to use the command line tool bluetoothctl, and it's found the USB dongle. So I'm going to turn scan on, and we just to make sure, we can actually go to and analyze what's being currently sent. And if we can look at the data, and we can see that our Arduino, with this happens to be its address, and it's sending that it has the counter service, that ramp counter service 1. So if we recall from our primary service, that C01 is the ramp counter service. So we then go here, we scan, and we should see, and that name that we had set in the code appears here, so that's that 58 again. So we just connect to it. And when we see, sometimes there, okay, now it connected. Sometimes there's problems with the Linux. I don't know why that always happens, but I'm going to now turn scan off, just so I don't get cluttered reports from other devices in the area. Oops. Oh. Okay. So we're in the GATT server. Now, to make sense of this in the Linux, it's helpful to know our database. And what this is saying here, this is an way that Linux organizes. It reads the GATT server database off of our device, and then it gives us a copy of it. And the way you can see that is when it says service 006, what that means is if we went to the database and looked at, and this is because I decoded this earlier from the over-the-air traffic, but if we look here, we can see things like our primary GATT service, that's at handle 6. If we look at handle 7, here maybe we can can do that, that we can see, or not too well, but so that service, that's that gap service that we had talked about. We can, or the GATT service, and so that's 6. And then when we get to here, service, so on the device, service A hex, that is our ramp counter service. No, actually, I'll just flip between the two. So that's the ramp counter with the UUID, and you can actually see that because if you see that it ends in the 01, that this is our 01. And now we have the characteristics that make up the service, and you can tell that because this characteristic has this service, and then the characteristic is 0B with B00. So 0B is that entry in the GATT server database right here, and that is our value handle. So that is our characteristic, the attribute that describes OC, which is the minimum value one. And our minimum value, we had assigned it B00. So we should see that, yeah, B00 right here. So this is showing another way of how this database is. You could then organize a database from either this information or from the over-the-air traffic. So what we're going to do is, now that we have our database, let's see if we can read some information from our Arduino. And here's just a cheat sheet. I took these and I just put, so I knew which commands were which. The way we do it, if we want to first look at those minimum values, if you recall in the code, we had set this to 253, so the maximum value. So what I'm going to do is I first go to the GATT menu, and then I'm going to select the, if you did list attributes, that would actually show you what we had seen earlier, but I'm going to select the attribute, this attribute, and then I'm going to say read, and FD, and then if we pull up a calculator, and we put it in programmer mode, we can see that FD is 253. So that's our minimum value there, or maximum value. Now what we want to do is let's look if the counter is actually changing. So the way to do that is we'll select the attribute, and then we'll read it. And it's 1, the minimum value, and it's 1, and it's 1. So it's not changing. What we want to do is we want to actually change it. So we're going to select this, and then we will select attribute, and then we're going to write a 01, which was that start counter. So we write that. And then we will, I'll just up arrow to select the read and then read it. And we should see DF11. And so the 13, 15. So it's once a second or so. And so we can see our counter increasing. We can then stop it by selecting the, let's see, 11, and then writing 00. And then we can read this. And let's see, so if we select our counter value again, and we should see that it's reading. Okay. So now if we want to look at the notification, the easiest way I've found to show that isn't with the Linux, at least I don't know a good way yet with this. The way to show for notification, let's say command notification, is I first select it with there, and then I'll use Wireless Protocol Suite to show that traffic coming over the air. And actually I'll show us selecting the commands too. That'll be kind of fun. So we'll go to Wireless Protocol Suite. We'll turn on the analyze. It's going to analyze, and this was all that ATT traffic that when the GATT server database was being read. So we're at frame 396. What I'm going to do is, oh yeah, and then there was some additional frames from this was when I was getting all those current values, and you can actually see the C19 and then 1B and 1D. So okay, so what I'll do here is I'm going to issue the command. We know that we have notification on ramp status, so we should be able to see if I start the command that we should get a notification that the ramp status has changed. But to do that, we first need to turn it on, and you can see that we have both the characteristic for the ramp status and then also this extra client characteristic. Notice that this is a special Bluetooth number, and that's the one that allows you to set notification. So the client, we said that we could allow the client to get notified automatically, but the client has to actually do it. And this is how the client does it, is first you select the ramp status. You could write to that descriptor, the client descriptor directly, but basically what we're going to do is we'll so you could write to those characteristic configurations directly, but we're going to let Linux do it. So we'll select the attribute, and then we will issue, let's see, oops, I forgot which, okay, so this is ramp status. So we're going to turn notify on, and there's a command. If you type help, there's a notify on command, and so we'll say notify on. Now what's interesting, right before I do it, I'll show you what's going to happen. So if we look here, the over-the-air traffic, we're reading, so we've last read a command, we're at frame of 15,560, and I turn notify on, and when we can see that there's a write request, that it's writing this data, and this 01 was setting that flag on for notification, if you recall from our discussion of that value is 01, and then this is just confirmation. So that actually turned on the notification in that client configuration descriptor, and it says notification started. Now what we can see is that since we've turned on the notification for the ramp status, that when we issue a command to start the ramp, start the counter going again, so we'll do that, we should see that it automatically sends the ramp status across the air. So we'll select this, and then we will write a start, and what I'll do then is just make sure I have that ready to go, is that we should see the when it starts the command, it will now automatically notify and send something over the air saying, hey, the ramp's started. So I'll write one to the command, say write start, and we see right here that, so this is where we did our write. So you see we took the command and we said, hey, ramp start. That was, you can see right here, that was that 01 that we wrote. And then the GATT server, the Arduino, responded with OK. And the Arduino also responded with a handle value notification saying, hey, the status, it's now running. And we can then also stop the counter. And when we do that, we can see that our issue of our stop command will be sent. We have it stop, and then and then the status, and it says that yes, it's stopped. So those are that's the notification there, and that concludes the demo of using the Arduino code.